All right, folks, this is the lecture on rolling without slipping. And sometimes that's how they describe a problem. They'll say a wheel is rolling without slipping, or they'll say it meets the no slip condition. So, not always 100% consistent, but it's going to refer to something about not slipping. All right, and then I love analogies. So, the analogy that's going to help you understand the motion of every single point on this wheel is thinking about being on a cruise ship. So, here is the cruise ship. Some people in one class were saying Disney cruise, and the cruise ship is carrying you through the ocean with a speed v. Assume that's constant. Because it's a Disney cruise, there is also a merry-go-round that you are riding, and that is making you rotate. So you are doing two things simultaneously. You are rotating and therefore have a tangential speed at every single point, and you're translating. Okay, and so your total velocity to a dolphin in the ocean is complicated because it's the sum of two different things. And so that's what this diagram is showing you. The wheel is translating through space, okay? But points on the wheel are also rotating. So your motion relative to that dolphin is this complicated shape. And as complicated as this function is, if you wanted to write it as a function, it really is just the sum of pure rotation plus pure translation. Okay, you don't have to write this down, but just the reason I'm making a big deal out of this is in the pulley lab, the pulley itself was only rotating, right? That axle was stuck to the ceiling. So the pulley had 1/2 I omega squared. Parts of the pulley had tangential speed because they could fly off tangent if they were a piece of mud or whatever. The two masses were only translating. So they had 1/2 mv squared terms. So this was only rotating, these were only translating. However, wheels on your bike, on a car, are both translating and rotating. So at some point in the slide deck, one of the things you're going to write down is, therefore, you have a single object that has both a 1/2 mv squared term and a 1/2 I omega squared term. It has both, even though it's a single object, because it takes energy to move that cruise ship through the ocean, and it takes additional energy to make the merry-go-round rotate. Those are not the same energy accounting.
Many students wonder what the path of a point on a wheel rolling without slip would look like. Today we're going to explore that and a little more. We have a spool. Many students wonder what the path of a point on a wheel rolling without slip would look like. Today we're going to explore that and a little more. We have a spool that will roll without slip on its inner radius on this track here. To track points on it, we have LEDs. So the yellow is exactly on the inner radius of the spool, and anything inside of that will act exactly like a wheel rolling without slip. The outer points will have more interesting paths that we will also track. In order to track the motion, we will use two techniques. One of those is long exposure photography, which will just show the end paths of the lights, and the other is video post-processing, which will attempt to track the light as it moves through the video so you can see how it rolls.
All of the curves traced will belong to the cycloid family of curves. The first curve is traced with the green LED at the spool center. Since the center of the spool should always be one inner radius from the track, the path is traced as a straight line, with slight variations from the curve of the track. The purple LED is between the spool's center and its inner radius. All such points will trace curtate cycloids, which look a bit like elongated sine curves, and will vary depending on the exact distance. The yellow LED is located exactly on the inner radius of the spool. It traces out a cycloid, where you can notice distinct cusps once every rotation. This is when the light has zero velocity, as it is at the no-slip point and instant center of the spool. The next two curves will be prolate cycloids. Prolate cycloids form for any point outside the inner radius and will have similar characteristics. First is the blue LED. Notice that the path starts to curl back on itself. The outermost path is the red LED, which looks similar to that of the blue LED. As the path loops back on itself, you can notice that at some points, this light actually has a negative x component of velocity, even though the entire spool is moving to the right. Finally, we will show all of the curves traced out together. In this way, a full family of cycloid curves can be seen, and intermediate curves are easier to imagine. This should show how seemingly simple things can contain an entire spectrum of interesting phenomena.